Today, we're going to learn how to convert the binary representation of floating point numbers into the decimal format so that humans can read it. Hello, I'm James Helfrich. Computers store real numbers in a format called floating point notation. This is sort of a scientific notation variation. How do you convert floating point numbers into the decimal version that humans can read? This video will demonstrate that. Recall that floating point numbers are stored in a format called IEEE 754. This notation divides the binary representation into three fields: the sign, the exponent field, and the significant. We can combine these, saying the real number is the sign, either positive or negative, plus 1 point, the significant, the 1 point is always implied, times 2 to the exponent. The exponent is stored in the exponent bias format. So the bias, which is what's stored in the floating point number, minus 2 to the width of the exponent field, minus 1. The process of converting a binary floating point number into a collection of decimal digits involves three steps. First, we're going to convert the binary floating point number into a fixed point number. Then we're going to convert the whole number component into an array of decimal digits. And finally, we're going to convert the fractional components into an array of decimal digits. The first case is when the decimal point is within the significant. In this case, we're going to divide the significant into the whole number component and the fractional component. In the second case, the decimal point is to the right of the least significant digit, in which case our fractional component will be 0, and our whole component will be all the significant digits plus a collection of zeros. The final case is when the decimal point is to the left of the greatest significant digit, in which case the whole point will be 0, and the fractional component will have perhaps a collection of leading zeros and then the entirety of the significant. Let's take a look at these three cases one at a time. So case 1, the decimal is within the significant. So if the exponent is greater than 0, or equal to 0, and less than the width of the significant bit, then we know the decimal point is somewhere within the significant. Then I'm going to say the width of the whole number is the size of the exponent plus 1, and the width of the fractional component is everything that's left. Now I'm going to make sure that my whole number has the correct number of digits and my fractional component has the whole correct number of digits. And then I'm going to walk through and copy the significant bits over to the whole point and to the fractional point. To demonstrate how this works, take a look at this floating point number. 0, which is my sign, which is positive. Then we're going to have 5 exponent digits, and then we're going to have 10 significant digits. And we happen to know this equals 42.5 in decimal, but let's see if that's correct. Now my significant is 10, 10 bits of width, and my exponent is 5 bits of width. And this is a standard 16-bit floating point number. Now my sign is 0, which means it's positive. My exponent will be the 10100 copied straight from the floating point part. And that's going to be 20, which is going to be 16, not plus 8, plus 4. 16 plus 4 is 20. But now remember, this is the exponent bias format. So I have to subtract the bias, which is 2 to the 5, which is with the bit, minus 1, which is 2 to the 4, minus 1, well, that's going to be 15. So 20 minus 15 is 5. And that's going to be my exponent. So I'm going to be 2 to the 5. And my significant is 0101010000 copied straight from the floating point number. And remember, there's always going to be a leading 1 point because this is a fixed point notation. So the question is, where does the decimal point go? Well, since the exponent is 5, we got to move it 5 places to the right of where it was. Remember, the significant was 1 point and then 010101, right? So if it is 1 point, we're going to move it 5 digits to the right of that, which puts it right about here, which means the whole number component is going to be 01010, and the exponent part will be 1000. Okay, so let's walk through the algorithm one step at a time. Now we'll make sure we're in case 1, which means the decimal point is somewhere within the significant. And then my whole width is going to be 5, which is my exponent. Plus 1 is 6, and that's the width of the whole component. And the fractional component will be significant width, which is 10, plus 1, which is 11, minus the exponent, which is 5, and that gives us 6. All right, so now I'm going to allocate a whole and a fractional component. Right now, they're uninitialized. And then I'm going to say the whole gets, remember, the leading 1, the 1, and then I'm going to copy over the width of the whole number of digits, which should be 1. and then 0, 1, 0, 1, 0, 1. You can see that from the significant. Everything to the left of the arrow, and don't forget the leading 1. And then the fraction is going to be everything after that, which is going to be the 1 and then 4 zeros plus 0. So here's the complete number, and then we're going to drop in the powers of 2 so we can make sure we understand where that works. And let's verify that this is true. So we have 2 to the 5 is 32, 2 to the 3 is 8, and 2 to the 1 is 2. 32 plus 8 plus 2 is 42. 2 to the negative 1 is 0.5, and the rest are zeros. So that's 42.5, and it does match. Okay, now let's take a look at case 2. Now the decimal number is to the right of the least significant digit. And this is going to be true if the exponent is greater than the significant, in which case my fraction part will be 0. And then I will copy over the whole component by taking all of the significant and perhaps a collection of trailing zeros. So here's my floating point number as an example. This is a 5,440.0, and we'll see if we can get to that same value. Now my significant is 10. The width of my significant field is 10. Remember, this is a standard 16-bit floating point number. And my exponent is 5. And so my sign is 0, which means I'm positive. And my exponent is 11011. All right. Now 11011, that's 16 plus 8 plus 2 plus 1, that's 27. But remember, this is the exponent bias format, so I have to subtract the bias, which is 15. 27 minus 15 is 12. And so 12 is my exponents. So I'm going to take that significant and raise it to 2 to the 12. So here's my significant. And don't forget, there's the 1 point, which is missing off there, which is this. Now, question is, where does the decimal point go? Well, it goes 12 slots to the right of where it is right now. And right now is all the way to the left of the significant field. So now when I move it over, I have to give myself 2 extra slots because my significant field is only 10 wide. But now the decimal point is 2 slots to the right of that. And so that's going to be my number. Okay, so here's my if statement. Am I in case 2? I am. And then my width of my fraction is 1. It's just going to have the value 0, and that's going to have the value 0. And this is where all the work is going to be in the whole component. So the width of the whole is going to be the exponent plus 1, which is going to be 12 plus 1 is 13. And then I'm going to allocate 13 bits, and then I'm going to set the leading 1. We have the leading 1 because remember, the significant field, there's always a 1 point, which is understood. Now I'm going to copy over all the significance, and then everything after that is going to be padded with those zeros. So when I put it all together, the complete number is this. Now let's drop in the powers of 2 so we can make sure we got the answer right. And that's going to be C here. That's 2 to the 12, which is 4,000 something, 2 to the 10, which is 1,000 something, 2 to the 8, which is going to be 256, and 2 to the 6, which would be 64, and add that all up and I get 5,440, and so I did in fact get the right number. Now the final case is when the decimal point is to the left of the last or greatest significant digit, okay? And it's going to happen when the exponent is less than 0. And that means the whole number component is just going to be 0, and all the significant is going to go in the fractional component. And how big is the fractional component? It's this width of the significant minus the exponent. So I'm going to allocate that space. I'm going to copy over the leading zeros as necessary, then the implied 1 dot, and then all the significance. So let's take a look at this number here. We have 0 as my sign and 0, 1, 1, 0, 0 as my exponent, and then actually the same significant I had in the last couple examples. Okay, so my significant width is 10, my exponent width is 5, once again using a standard 16-bit floating point number. My sign is 0, which means I'm positive. My exponent would be 0, 1, 1, 0, 0. Let's see here, that's going to be 4 plus 8, which is going to be 12. But remember, we're in exponent bias format, so it's 12 minus 15 is going to be negative 3. And since that's negative, we're going to be in case 3. My significant field is the same as I had before, right? And that's going to be, don't forget the implied 1 dot, 0, 1, 0, 1, 0, 1. But now, in order to get the fixed point notation, I got to move to the decimal point to the left 3 spots because it's negative. So I got to drop the 0, 0, and don't forget the implied 1, and that's where the decimal point is going to go. So that's going to be 0.0010101, and so on. Okay, so Here's my if statement. I am in fact in case 3. My whole is going to be 0 because my entire significant is going to be to the right of the decimal point. And then my fractional width is significant minus exponent. And since the exponent's negative, I'm going to take the, it's going to be greater than the significant, which in this case is 13. And then I'm going to set those to empty. Now, I have all my leading zeros. In this case, I have 2 leading zeros. And then I have my implied 1. And then I copy over the entirety of my significant. All right, let's verify we have this right. The whole number is 0, and then my fractional component is everything else. We'll drop in my powers of 2 so I can verify this. And then let's see here, 2 to the negative 3 is 0.125, 2 to the negative 5 is 0.03125, 2 to the negative 7, 2 to the negative 9. And if you add that whole thing up, we get, in fact, our number. Okay, so after we have our fractional and a whole component, then we have to display the whole number. Well, all we have to do is display the whole number and put a decimal point after that. That's super trivial. And this will only work basically if we have an integer type that can handle an arbitrary number of digits. We can learn how to do that in another video. Now we have got to convert the binary fraction into decimal digits, okay? And let's say this is my fractional component. And so that's going to be 2 to the negative 1, 2 to the negative 2, negative 3, negative 4, negative 5, okay? And that's going to be 0.5 plus 0.125 plus 0.0625 plus so on. But notice how I'm representing this with 5 digits. So it's not 0.5, but 0.50000. You'll see why I did this in just a minute. It's going to make the math a little bit easier here. So my algorithm is to have a result, which I want to display as one big integer. And I also want to have a power of 2. And this can be the 0.5, 0.2. 0.25, 0.125, 0.0625, and so on. I'm going to keep dividing by 2, divided by 2, divided by 2 with this and adding it on to my summation. Now, I'm going to start with my first power of 2, which is 0.5, okay? And then I'm going to go through and I'm going to add that power of 2 to my result if I have a 1 in that location in the binary representation. And then I'm going to display the results. So to demonstrate how this works, we're going to have the same numbers we have here, 1, 0, 1, 1, 1. And my result is going to be 0, and my power of 2 is going to be 0 because I'm going to initialize it as empty. And then I'm going to say, hey, my initial power of 2 is 50,000. Notice that corresponds to the 50,000 we have up above. And that's really important because we're going to see if we're going to add that value onto the result if there's a bit there. Now we're going to walk through my fractional component. So I'm going to start here at 2 to the negative 1. Then I'm going to say, hey, are you 1? And if you are true, you're a 1, then I'm going to add the power of 2 onto my result. And my result was 0. Now it's 50,000. Now I'm going to take my power of 2. I'm going to divide it by 2, which is going to be 25,000. All right, you go back up here again, advance to 0. Notice I have a 0 in this case, which means I do not add to the result. I go straight to the power of 2 and divide it by 2. Then I go back up to here, advance it. Now this guy is a 1, so I'm going to add it onto result. So 50,000 plus 12,500 is going to be 62,500. And then I'm going to divide my power of 2 by 2. And then this guy is also 1. So I'm going to add 62,500 onto there. And then I'm going to subtract my power of 2. Then I'm going to go back up here, my last one, and that's also 1, so I'm going to add it onto the result. And then I'm going to advance my power of 2, but I don't actually use it. And when I'm finished, I will display 71,875. Now notice how I keep it all as one big integer because I already displayed the decimal point in step 2. Let's go through a couple examples here. First of all, I have this 16-bit floating point number, which looks kind of random, but let's see what this is in decimal notation. Okay, so first of all, I'm going to convert the binary floating point number into a binary fixed point number. So my significant is 10, my exponent is 5, because this is a standard 16-bit floating point number. But realize I can do this with any significant width and with any exponent width. I can have a significant of 1,000 bits if I want, and it's going to work all the same. Okay, so my exponent is the first, well, it's not the first 5 digits. The first digit is the sign, but the next 5 digits would be 1 and then 4 zeros. And that's going to be 16. And then there's no 8, there's no 4, there's no 2, there's no 1. So it's just 16 minus my exponent bias, which is 15, which is going to be give me 1. And my significand, don't forget the leading one, is everything else. It's the last 10 digits. So my whole number is going to be 1, 1. Why is that? Because my exponent is 1, and therefore I'm going to move the decimal point to the right 1. So I'm going to have the implied 1 plus the most significant field of the significant bit, and that's going to be 1, 1, base 2. And my fraction is going to be everything else from the significant, 0, 0, 1, 0, 0, 1, and then 0, 0. So that's my fractional component. Now I'm going to display the whole component, which is going to be 2 binary digits, 1, 1, and that's going to be 2 to the 1 plus 2 to the 0, and that's going to be 3, and that's going to be my whole component. Don't forget the dot. And then my fractional component, and that's going to be, let's see here. The first 0 is going to correspond to 2 to the negative 1, which is 0.5, but I'm not going to add it because that's a 0. The next binary digit would be 0, which would be correspond to 0.25. But once again, there's a 0, they don't add it. But I do add 0.125. I don't add the 0, then I add the 0.015625, and so on and so on. When I add the whole thing up, I get 140625000, and when I display it onto the end of my 3 point, I get 3.14. And this is actually the closest representation we have to pi for a 16-bit floating point number. Here's another example here, 1100100 and so on. What is this in decimal? Oh, right now I have absolutely no idea, but let's take a look here. First of all, I'll convert the binary floating point number into a binary fixed point number. So my significand is 10, my exponent is 5, it's a standard 16-bit floating point number. So my exponent is going to be 10010, which is all the bits, it's the first 5 bits except for the leading one. And that's going to correspond to 16 plus 2 is 18. 18 minus my exponent bias, which is 15, which is going to give me 3. So my exponent is 3, 2 to the 3. My significand, don't forget the 1 point, and that's the last 10 digits, okay? So my whole number, well, see, my exponent's 3. I'm going to move the decimal point to the right 3 spots. So this would be 1001. Forget, my leading bit is 1, so I'm negative here. So it's negative 1001. That's my whole component. And my fractional component is everything left in the significant, which is 1100111. All right, now that I'm going to display the whole component, let's see here. That's negative, don't forget. Sorry, that's 2 to the 3, which is 8, not 2 to the 2, not 2 to the 1, but 2 to the 0, which is 1. So 8 plus 1 is 9, and it's negative, so it's negative 9. So I'm going to display that. And then my fractional component is going to be 1100111. 1 corresponds to 5 million, and then the next one corresponds to 2,500,000. And then I skip the next 2 because they're zeros, and then 312,000, and so on, add that up as 8750000, and then I'm going to append that onto my negative 9, and this is negative 9.8. This is actually the gravitational constant for the polar gravity on the Earth on average. My last one is 0110011, and so on. What does this correspond to? Well, let's find out. First, my significand is 10, my exponent is 5. So my exponent is going to be 11001, which is 16 plus 8 plus 1 is 25. 25 minus my bias, which is 15, and that'll give me 10. So it's 10 base 10, and that's my exponent, which means I'm going to move the decimal point to the right from its default location in the significand. So my significand is 1 point, and then the last 10 digits, and that's going to, and don't forget, I got to move the decimal point to the right, 10 digits. So basically, I'm taking the whole significand and put it in the whole number component, and which means the fraction component is going to be 0. Now I'm going to display the whole component, and the whole component is 2 to the 10 plus 2 to the 9, not 2 to the 8, but 2 to the 7, 2 to the 6, and so on. Add that all up, and it's 1776. So I'm going to display 17 to 76 point, and then by the fractional component, but the fractional component is just 0, and that's 1776, and that's going to be the result of that floating point number. Okay, so let's try this on your own here. Here are 5 floating point numbers, all in the standard 16-bit notation. Try to see if you can figure out the decimal value associated with each. You can look up a variety of decimal to floating point converters online to check your answers on this. You can learn more about this by taking a look at the output section of the floating point chapter of the C++ data structures textbook.